So we've talked about how you can use stoichiometry with grams, converting grams to moles, and then using that stoichiometry of the balanced equation to convert from moles of one thing to moles of something else. And then we've also talked about how you can use the concentration and the volume to get moles, and then also do stoichiometry. So now we're going to look at a couple of examples involving gases and how we can use gases with stoichiometry as well. So we know that obviously with gases, we've got the ideal gas equation. We've got to find the moles of a gas, we do use the pressure times the volume over the gas constant times the temperature. And we can find that equal volumes of a gas at the same temperature and pressure will have the same number of moles. Or what that means is that basically if you have different gases, but all four of these variables are the same, if all the gases are in the same container, and they have the same temperature, and they have the same pressure, then of course all of the gases have to have the same number of moles as well. And then another thing we learned about gases is that we do have gases that many times are at standard temperature and pressure. So we can see that at standard temperature and pressure, because the gas constant doesn't change, the only two variables that can change at STP are the volume and the moles. And so we learned that the molar volume of a gas, or that 1 mole of any gas at STP, will have a volume of 22.4. And that sometimes makes your math, especially on a multiple choice question, makes your math much, much easier. So let's look at a couple of examples that may involve this 22.4, and I'll show you a couple of different ways that you can solve those problems. So first of all, we need to balance the equation above. So we got a bunch of hydrogens all over the place, so I'm going to skip those. 1 nitrogen, 1 chlorine, 2 chlorine. So I'm going to put a 2 there, and that does now make 2 nitrogens, so I'm going to put a 2 there. 1 calcium, 2 oxygens, and here we only have 1 oxygen. So we'll put a 2 right there. Now, typically when you fix everything else, hopefully that fixes the hydrogens as well. 2 times 4 is 8, plus another 2 is 10, and then we have 6 plus 4 is 10. So that is a balanced, the equation is now balanced. Okay, so it goes 2, 1, 2, 1, 2. So part B says calculate the mass of ammonium chloride required to produce 11 liters of ammonia gas at STP. So right away, they're giving us the volume of ammonia gas. So ammonia is NH3. Okay, I didn't clarify that. Sorry. Ammonia is NH3. Ammonium chloride is the NH4Cl. So if you have 11.6 liters of ammonia gas at STP, remember, STP means the temperature is 273 and the pressure is 1 atmosphere. So you can use PV equals nRT, and you can find moles that way by plugging all of the numbers into the equation. Or you simply take 11.6 liters of NH3 and use that equation, or the conversion, 1 mole equals 22.4. So we can say 22.4 liters equal to 1 mole. And see how easily we go from the volume of a gas to the moles of a gas? Now I just take 11.6, I divide by 22.4, and I get 0.518 moles of NH3. And now, guess what? It's just like I took grams and converted to moles. It's just like I took the concentration and the volume and I converted it to moles. Now I have the moles of NH3. So now I can do any stoichiometry problem that they ask me, converting NH3 to anything else in that balanced equation. Okay, they're asking for ammonium chloride, so I'm going to convert moles of NH3 to moles of NH4Cl. But the key to all of these, whether you start with grams, whether you start with concentration and volume, or whether you start with the volume of a gas, is you have to get to moles. Stoichiometry does not work if you aren't in moles. You cannot do this step with anything other than moles. Okay, so my moles of NH3 are 2. My moles of NH4Cl are also 2. And since they're asking for the mass, I'm going to put 1 mole of NH4Cl on the bottom. And then I look at the molar mass. It is 53.5 grams per mole. So really, I'm taking that 0.518, and I'm still using the answer that's on my screen when I divided 11.6 by 22.4. Even though I wrote down 0.518, I'm really going to use 0.517857143 because that's what's on my screen. That's the best answer to use, is the non-rounded number. So I'm going to it's probably still going to give us the same answer. I get, I'm sure you got this too if you use 0.518, 27.7 grams of NH4Cl. Okay, and again, the key there is knowing whether I use 22.4 or whether I take the pressure and put 1 atmosphere and the volume 11.6 liters, divide by R 0.08206, divided by the temperature 273 Kelvin. If I do all of that, guess what, guys? Guess what answer I get? 0.518 moles. So using 22.4 when you know you're at STP is a really, really easy and quick way to convert from the volume of a gas to the moles of a gas. Imagine a multiple choice question. Of course, they're not going to expect you to be able to do this. But let's say you had 44.8 liters. Would they expect you to be able to take 44.8 and divide by 22.4 and get 2 moles? Of course they would, okay, without a calculator. Okay, let's look at this next example. Okay, it says balance the equation, 1 barium, 1 barium, 1 carbon, 3 oxygens, 1, 2, 3 oxygens, already balanced. So part B says calculate the volume of carbon dioxide gas produced when 9.85 grams of barium carbonate is completely decomposed in the reaction above at STP. So the only number they give us is 9.85 grams of barium carbonate. And again, anytime they give me grams, the only thing I know what to do with that is to convert that to moles. So I'm going to take the molar mass of barium, the molar mass of carbon, and then 3 oxygens, and get a mass of 197.3 grams per mole of barium carbonate. And again, what do I have now? I have moles. So now I can go from moles of barium carbonate to moles of, what are they asking me about? They're asking me about carbon dioxide, so CO2. And then remember, it was already balanced, so it is just a 1-to-1 ratio. Now remember, at this point, I could get grams of CO2. I could do another step here. I could go 1 mole of CO2, 44 grams. But I don't need grams. If I get grams of CO2, that's fine. But then I'm just going to have to convert them back to moles to do this last step. So why would I do that? Why make myself do an extra step to do another extra step to convert it back to moles? It doesn't make sense. So 9.85 divided by 197.3 equals 0.0499 moles of CO2. And now that I have moles of CO2, now I can use the equation. Again, I can use PV equals nRT, but anytime I see those 3 letters together, STP, the first number that pops into my head is 22.4 liters equals 1 mole. Okay, and that should happen for you as well. Okay, STP, usually when they tell that to you, you're going to be using something involving 22.4 liters. Okay, because now, just like converting moles to grams, I can go 0.0499 moles of CO2, and then I'm going to say 1 mole of CO2, 22.4 liters. Okay, so I'm going to take that number that's on my screen, multiply by 22.4, and I'm going to get 1.18 liters of CO2. Okay, now, could I, instead of even stopping right here and getting an answer, theoretically, could I, just like I could have converted moles to grams, could I have just kept going here and said 1 mole of CO2 has a volume of 22.4 liters? Absolutely I could, okay? And that still is obviously going to give us the same answer of 1.18 liters. Because remember, the whole time we're doing this, we're trying to cancel our units. And if we've done it correctly, that's liters of O2, Once you have the correct units for volume and it's CO2 rather than BaCO3, then absolutely yes, you can use that, okay? Just like converting moles back to grams, or just like converting moles to molarity or moles to volume using concentrations, of course you can just do 1 mole, 22.4 liters when you know it's a gas and you know you're at STP.